So we're starting off with f prime graph. And we're going to pull information so that we can create a slope sine line. Okay. So how do we begin marking this derivative graph? Do you remember? Yeah, above, below, and on the x-axis, right? The key thing right now is don't pay attention to how the graph is moving. Just pay attention to where the graph is located. We'll do the movement when we get to the second derivative sine line. So what numbers do we want to put onto our sine line? Yep, -4. I know it's a little bit off -4, but we'll treat it like -4. Yeah. Yeah. No, we don't, but we'll just treat them like endpoints. That's where the graph ends. So there's my slope sine line, or f prime sine line. Okay. What behavior is our graph going to have in terms of its slope? Positive or negative? Yep, because I know it looks like it's decreasing, but we don't care about that. We're just going to see where it is and look at what symbol to put. Decreasing. Yep. Increasing. Because it's above the x-axis and finally below the x-axis. Yeah. Hey, LJ, just want to make sure, can you hear me?
Yes, I can.
Okay, great. Okay, so that's our f prime sine line. We'll sketch the graph in a moment, but let's create the second derivative sine line. Okay, so where do we look to find our second derivative sine line? It's going to be, yeah, now we're looking at the peaks and valleys. Okay, the peaks and valleys is going to, this is not normally where points of inflection is located on the original graph, but this is where it's located on the f prime graph. That's right. On the original graph, it'll look more like this. Point of inflection looks more like this, where the graph, where's that change from one concavity to the next. All right, so this is where normally POIs are located, but on the f prime graph, it's located here. So you can imagine f prime graph is kind of like the steepest part of your graph, and that steepest part of the graph is located here on the f prime graph. Okay, so -5 as the endpoint. Okay, so now that, actually, I'm going to share this worksheet with you since you're following along. So give me a second here. Session. Where did I find it? Where did I put that review sheet? Okay, here we go. Okay, LJ, I put the links in the chat box if you want to access it.
Okay, thank you.
Uh-huh. All right, so back to our F double prime graph. What's occurring here between -5 and -3? Concave up or concave down? Good, so now we look at the slope. Wherever the slope is becoming more negative, the original graph is going to have a concave down shape to it. And it's going to keep flipping back and forth. Right here, positive slope means concave up on the original. Negative slope, concave down. Positive slope, concave up. Okay, good so far. Now, we're just going to sketch a graph that has this shape to it, okay? And the thing is, don't get caught up with the x-axis, okay? Don't feel like you got to connect a point to the x-axis. We just want the graph to visually have those peaks and valleys at these points, okay? So your graph may look a little different from mine, which is fine, but we're going to do 2 layers of this. We're going to create a first layer just with a shape, and then we'll go back and give it the curvature of the property here. So I'm looking at this graph and I'm thinking, okay, I want a relative max at -4, so I'll try to target a point that is a little higher, maybe. At -1, I'm expecting a relative min, so it doesn't really matter where I put it. Maybe I'll just pick a point that is, maybe I'll pick a point lower. Doesn't really matter, right? I just want a relative min. It doesn't have to be a certain height or certain y value. And then at 3, I want a relative max. Good. Oh, it doesn't matter. One could be higher, one could be lower, but as long as we have relative max, that's all we care about. So your graph may be higher or lower than mine, but it should have the same general shape. Good. Okay, so I put it dotted lines because I know that's not my final product, but it does give me a place to start, right? Doing 2 things at once is just too much. Being able to update a version is a lot easier, a lot more manageable. So the next thing is we want to start plotting points of inflection, okay? And you may be thinking, wait, where do I find these points of inflection? Just plot them along the path of the graph. So wherever the graph lands at -3, just go ahead and highlight that point. We're going to force it into a point of inflection. So maybe yours is a little bit higher or lower than mine, but it should be, it's just along the path of the graph. At 1, I want another point of inflection. So wherever the graph lands at 1, And then where the graph lands at 7. Okay, so I should extend this graph a little bit more. I'm not going all the way to 7 here. Good. So now we're just going to connect the dots from our graph with the appropriate curvature. So I'm going to start off with concave down to my first POI. Then I'm going to flip it. I'm going to keep changing the curvature from one to the next. So first up, concave down. Right. Switch it over to concave up. Switch it back to concave down. And then switch it back to concave up. Now concave up, do I make the graph go back up? No, it's got to follow along this path. So the best I can do is to give it a concave up curvature, but I still got to maintain this negative slope. I can't all of a sudden break that negative slope and make it go up here. It's got to be in the general path along the original graph. So that kind of helps ground me a little bit so I don't just go out of turn here. Okay, how's that for you? Good, okay. So now let's move on to the second derivative graph. The second derivative graph, all we care about is looking at this and converting it to be our graph. So we're going to create a similar graph with notations, but now we're going to put concave up, concave down, and we'll put POI here. Okay, where do we place these points of inflection? Yeah, on the x-axis, yeah. All right, so where do we start? Okay, bottom. Well, we got to make it rise, right? These points kind of help guide us. We know it has to rise to that point, otherwise we're not going to be able to connect these points together. Then above, loops back down, below, loops back up, and finally it's going to end up above. Okay, how is that? Oh, so concave down, concave up, concave down, concave up. So all of these properties are accounted for. Okay, now try one on your own, see if you can. Okay, so try number 2, and we'll walk through it after you try it. LJ, let me know if you have any questions as well.
Okay, thank you.
Okay, Nuria, let me know. How does that look to you? Is that what you got? Okay, good. Second derivative sine line. Take off your peaks and valleys. Okay, what you get? Yep, now we're looking at the slope. Look at the slope, yeah. It's going to keep back and forth, right? Okay. We'll sketch our graph, make two versions of it. So before I start the graph, I'm just going to kind of target what I want to go after. I want a relative min somewhere down here. What would you call -2? Or what's happening at -2? Okay. Is it a relative max or relative min? No. However, what's going to happen here, though, in terms of the graph? What would the graph look like? Okay, goes through, but it's going to have a momentary, what? Slope of 0. Yeah, so it's going to kind of rise, kind of flatten out for a moment, and then rise again. So I'm going to target a point so I can kind of get that momentary leveling off for a moment, and it's going to continue rising to a relative max at 5. And it's going to begin its descent down. Okay, so at least we have something to work off of. It's not perfect, but it really helps us with the next step. Okay. So your graph should mirror what your arrows are telling us. And then don't worry about the x-axis. Nothing is significant about the x-axis here. We just want the graph to rise and fall based off of what you see the arrows are doing. Okay, what's next? Yeah, let's get those points of inflection, right? So just follow the path, the graph. Where's -5.5 going to land? It's around here. -2, 3, and it's going to end at 5. Oh, sorry. It's going to end at 6. Sorry, 6. Okay, we have 3 points of inflection, right? So now we're just going to go back, retrace, and get the curvature to match what we see here. Concave up. Transition at the point of inflection to a concave down. Transitions to a concave up. And finally transitions back to a concave down. Good. Okay, let's create our second derivative graph. Okay, x-intercepts, right? Okay, so it's nice to put those points down, kind of anchors our graph a bit. We know where our graph is going to have to go through as we move in, as we sketch each of the parts. Okay, where do we start? So where is that graph going to be? You can start up here, right? Yeah, you can start because you want concave up to be in this region here. But it's going to have to decrease because we have to link up to this point here. And then, so below, right? Above and below. Okay, should feel pretty comfortable now, right? Getting from F prime to, okay, so we'll definitely do some more practice in class tomorrow. Let's do some optimization. How's that? So let's go to your packet. We have some extra problems that we may not be able to get to in class. Let's try page 18. Okay, so page 18, we have a rectangular storage container with an open top, volume of 10 cubic meters. The length of its base is twice its width. I'm going to say width here. Material for the base costs $10 per square meters. Material for the size costs $6 per square meters. Find the cost material for the cheapest container. So the hint is that we're optimizing, minimizing surface area. Okay, let's draw our box here. Okay, so we're trying to optimize surface area. So we got to build our surface area formula. Surface area, we're just adding up the area of the surfaces. What's the area at the bottom? Yep, that's 2x squared. Nothing up top, so there is, if it's a closed box, we would also need to include 2x squared up here, but nothing up top. And then we have 5 faces total, right? We also have vertical faces here. What's the area of this side? How about x times h? Right, it's rising up, right? There's a vertical side there. So I have x times h. Is there another x times h on this side, right? So those are the side verticals. Those are the vertical sides. Okay, what about the front-facing sides? But it's going to be 2x times h. Yeah, 2x times h, right? Because it's going to be rising up vertically. Okay, so we have each of the areas accounted for. 1, 2, 3, 4, 5, right? 5 sides. Right, because we're trying to optimize surface area. We're trying to figure out what will allow us to because we know the volume is going to be 10 cubic meters, right? That is a given. But we want to create the box in a way where it doesn't matter what the shape of the box is. We just want to be able to save money, right? We just want it to have 10 cubic meters of space inside, but we want to organize it so that we can spend the least amount of money on building these boxes. So we have cost associated with surface area. So surface area and cost are very much related to each other. So the base costs $10 per square meters. So know that this piece is going to be a $10 component. Okay. But the sides have a cheaper material. It's only $6 per square meter. So this is going to be $6 related. So here's my cost equation. My cost equation is just merging surface area with the dollar amount. Okay. So I can multiply these. What does that give me? Maybe I want to merge these first here. So xh plus xh plus 2xh plus 2xh, this equals, yeah, and if I multiply that by the dollar amount. Okay, so I'll put this is where the star really goes. We really are trying to find a derivative of that cost equation. Okay, any questions so far? Okay, we want to find a derivative, but what's the issue right now? What's making it difficult for us to go through? Yeah, that h. That h is sticking out like a sore thumb. We have to find that h to be replaced in terms of x. So this is where volume comes into play. The volume is going to help us make that substitution that we need to move the problem forward. So what's the volume of this box? Okay, yeah, 10 cubic meters. What's the volume in terms of this formula? Yep, which is Yep. So now, like you said, there's a volume value, right? We have 10. You see things beginning to, come together here. What can we do next? More than, what do we want to get by itself? You want that h. You want to divide by 2x squared. Yeah, so the x squared is going to end up being the denominator. We can reduce, right? 10 over 2 can reduce, but the x squared is not going to go anywhere. So insert in for the h. All right, how does that look? All right, so now what do we want to do here? Yeah, let's get it cleaned up so that we can find the derivative, right? But things are a little bit messy right now. We want to try to get all the numbers cleaned up. We want to get the variable to be moved up to the top. And then we can do power rule. Then we can find critical points, and then we can solve for x. One of the x's cancel, well, x and x squared cancels out. There's an x remaining in the denominator, but I want to do some more movement here. I don't want to have to go through quotient rule. I want to just bring it up and do power rule instead. Divided by x squared. I took out one of the x's, and I'm left with that x in the denominator, and now I'm pushing it up. Now we can find the derivative, right? C prime. X to the, good. And what do we do with all of our derivatives? Equals 0, yeah. Just like finding a critical point. Okay, so now that's equal to 0. I'm gonna bring that x squared back down. Now I'm just gonna move things around and hopefully maybe cross multiply and work my way to solving for x. Now it's just a algebraic equation here. I cross multiply here. So now I'll take the cube root. Normally, algebraically, it would, but we're trying to figure out dimensions, so we'll just drop the negative. Yeah, negative is not going to make sense for the context of our problem. So cube root 9/2, 1.651. Okay, but what is the problem asking for here? We have the x value, but it's asking for the cost. Say it again? Yeah, it's cost, right? Yeah, so there's a lot of variations, right? You got to put in this one or this one. There's like 4 different variations. Just don't put into C prime. Okay. So pick the easiest one to plug in. Maybe I'll pick this one, the 20x squared over 180x. Yeah, any version is fine. Mm-hmm. Okay, how do you feel about that one? It's a lot, right? Yeah, that's true. But I mean, ultimately, I'm looking at the work. If something throws you off, but the rest of your steps is right, I'm not going to give you no credit. I'm care more about your understanding of the concept. So that's, to me, it's pretty minor. But if you understand the steps, that's what's more important, that you can at least try to get some version of the equation, understand there's a supporting equation involved, plug that in, get it ready for power rule, find the derivative, set equal to 0, solve for x. All right, more concerned about the steps. Okay. Okay, that's fine. That's, yeah, I mean, basically just wanted to be able to get through a derivative graph and optimization, and we'll do some more of these tomorrow. Okay?
If you want to continue, I'll just watch the recording.
Yeah, sure. LJ, do you have any questions, or do you want me to go over any specific problem?
No, I was just wondering if you want your practice with the drawing the graphs, because that's kind of what I struggle with most.
Wait, say it again?
I was just wondering if you had any like extra practice for the drawing of the graphs.
Got it, yes. Yeah, so if you look at, I don't know if you got a chance to print it out, but if you looked at that handout that I put in the link.
Okay.
Uh,
Get off that one.
you got
I
this one, okay.
get one
And
up.
then 3 and 4, I think these are good ones too.
Okay.
How'd you do with 1 and 2? Were you able to try these?
I did okay. I get confused on just like finding the points and like which points to use for the sine lines.
So are you good with the sine lines?
No. That's kind
Oh,
of
okay, okay. Yeah, go ahead. Yeah, we can do that tomorrow morning or Thursday morning. Okay. Uh-huh. So back to number 1. If I want to kind of create my f prime sine line, I start off with my x-intercepts because I want to get my slope zeros onto my graph.
okay.
So -4, -1, and 3.
Okay.
I like to label my above and below because I can just look at my graph. I'm not even going to pay attention to how the graph is moving. I just want to know where it's located. So if it's sitting above, I want to assign it as a positive slope. If it's sitting below, I want it to be a negative slope, above positive and below negative.
Okay. How can we include the 9 and the -5? Is that just because it's like the endpoint?
Yeah, it's the endpoints, right.
Okay. Okay, that makes a lot more sense. I was like confused where to look and like why we were like including those, but now I get it.
Okay, what about the second derivative sine line?
So wouldn't it would be the -5 and the 9.
Mm-hmm.
Don't you do the points of interest?
Yeah, points of inflection.
Oh, inflection.
But
That's
these points of inflection normally don't look like these. Right? Normally, they look like the transition from one concavity to the next, right? Concave up to concave down. But the reason why they're located here as relative max and mins is because we're looking at the derivative graph. So points of inflection is going to be located in a different slot.
okay. So if it was like the regular graph, it would be like the -1 and like 3.
That's right. That's right. If this is the original graph, just let you know that on the test you're going to be given a derivative graph. So, but yeah, you're right. Normally, yeah, you'll be like, oh, concave up, concave down, concave up, right?
Okay.
All right, you're good with assigning concave up, concave down from the f prime graph?
Yes. Yeah, honestly, it was just like finding the points that I was struggled with. Okay. Thank you, Mr. Yang.
Okay, so you're good?
Yeah.
All right, I'll see you tomorrow.
And okay, it's at 7:30.
Yeah, so
right?
tomorrow, 7:30, I may focus more on the quiz material, and then yeah, I'll keep going back and forth depending on what students want to do.
Okay.
Okay, all right, see you tomorrow. Okay, bye.